Welcome to Climate Now, the podcast that explores and explains the ideas, technologies, and solutions that we'll need to address the global climate crisis and achieve a zero-emissions future. I'm James Lawler. To sign up for our newsletter, which goes out every Tuesday morning with the link to the latest podcast episode, background information, and relevant links, go to climatenow.com. To get in touch with us, email us at contact@climatenow.com. We love to hear from our listeners. On today's episode, I'm speaking with Dr. Sue Natali, an Arctic ecologist at the Woodwell Climate Research Center, about the impacts of permafrost thawing on the global climate system. But first, our news segment, This Week in Climate News. This week in Climate News, I'm joined by Julio Friedman, Dina Capiello, and Darren Howe. Welcome, guys. Great to all be together again. It's been a while.
Yeah, it's great to have all of us.
So, the Brain Trust this week is commenting on an exciting list of news articles. The first one is that the California Air Resources Board has unanimously approved an advanced clean fleets rule.
This is a really interesting development. First of all, these are some fairly aggressive targets. Essentially, some of the lighter duty commercial fleet vehicles need to be at least 10% electric by 2025 and 100% electric by 2035. For much larger vehicles, sleeper cab tractors, etc., they have to be 10% zero emission by 2030 and 100% zero emission by 2042. So these are quite aggressive targets. But why this is important is because on a per vehicle basis, these commercial vehicles travel many more miles and generate far more emissions per vehicle than passenger vehicles. So on one hand, the growth of the industry is actually quite impressive. I was just at ACT Expo last week, and I have to say just the number of zero-emission vehicles, whether it's electric, hydrogen fuel cell, or low-emission vehicles, CNG, was stunning.
And this is the ACT Expo stands for the Advanced Clean Transportation Expo, and next year it'll run from May 20th to 23rd, for all those interested.
Yeah, I've been going for a few years, and this, there's so many options available for purchase today. Over, 120 models that are being produced and delivered to customers, 35 manufacturers selling in North America across the range. That being said, a lot of these products are not yet ready for actual commercial use, and folks have expressed some frustration with the timing of this mandate. So some examples I've heard, a lot of these electric TRU units, so think of your reefer refrigerated trucks, those are all undergoing testing. There's nothing that's actually being sold today. There was a panel where Cisco and PepsiCo were also saying, hey, people haven't focused enough on Class 6 trucks. There aren't many on the market, if at all.
If you were a fleet owner operator, could you go and buy electric trucks today?
Yes, you could, and they're available. I think the big challenge is the cost. So a typical truck might cost $150 to $250K if it's really, really expensive. But a battery electric truck can cost, $300,000 to $500,000. So you're talking about, 2.5 to 5 times the cost from an ICE equivalent.
Do they have customers yet for these models at such high prices?
It's a great question, James. They do. And part of it is really kind of the mandates that are coming in. So the mandates are having an effect. One thing that you see is actually a lot of the larger fleets are bulking up. But I think the question here is what about the smaller players? The vast majority of trucking companies in the US have fewer than 20 vehicles, some as few as, 6 vehicles. These players don't have the cash flow that allows them to buy these expensive trucks off the bat. So what we've seen is the emergence of a new type of company that offers fleets as a service. We're seeing companies like Zeem, Ford Mobility, Watt EV. They're saying, hey, we're going to get some infrastructure finance partners. We're going to buy the charging infrastructure and the trucks, and we're going to lease them back out to these smaller companies that otherwise can't afford to put up that cash up front.
Yeah, and it's important to find solutions here. As this article in Canary Media notes, these trucks that we're talking about are 7% of vehicles, but are responsible for more than half of the smog-forming nitrogen oxides and other health-harming, I'm quoting the article, fine particulate pollution from vehicles. So we're not just talking about CO2, we're talking about, air pollution, air quality in a much broader sense as well.
So I can't help but on the heels of this story, put in a plug for my colleague Mike Roth, who I'm sure was at ACT.
Absolutely.
Who's head of the North American Council for Freight Efficiency. So
who's been a guest on Climate Now. Wonderful episode.
He's amazing. But he's actually going to run in conjunction with RMI this coming September, the next Run on Less. And it's actually studying some of the barriers to electrification of trucks in general. It's going to be called Electric Depot, and it's going to be all around scaling and particularly around 8 separate fleets.
Shall we move on to this story about the renewable natural gas investment?
I'm chuckling at renewable natural gas.
We can pause and appreciate the humor of that title, of that name, and then move on.
I just find it interesting, and it harkens back to, the push by many of these same companies, the oil and gas industry, to embrace ethanol, right, from corn crops.
The article does mention that in California, renewable natural gas from dairy methane, so these are cows producing methane, and if you capture that methane and you sell it, that can be considered carbon negative under the low carbon fuel standards.
The reason why is because methane is so much more potent a greenhouse gas that if you are avoiding and reducing methane emissions, even if you are creating CO2 emissions, it is in fact counted as carbon negative. We'll see how long people agree to do that. At some point, avoiding methane emissions will no longer be considered additional.
Makes sense.
Julio, one of the things that I was thinking about as I was reading this article, and I want to know what your take is like the very companies that are investing in this, right? The oil and gas companies, pipeline companies, are ones that suffer from a lot of methane leakage now from their gas production and transmission. So to me, and this is the environmental NGO perspective, right? It's why not use the gas that you're wasting into the atmosphere for some of these very same purposes? I mean, and methane is methane, right? Regardless of where it comes from.
Yeah, I really count these in my brain in two very different ledgers. Let me agree with you that oil and gas companies need to be far more aggressive in reducing fugitive methane emissions. That actually is also something which should just be mandatory and will no longer be considered additional soon, because we simply can't allow it. And the IEA put out a report just last week detailing how cheap and easy and impactful managing methane emissions in particular would be. It is also the case, though, that people need more energy. If you can turn waste food into a renewable natural gas, that's great. And in many cases, the people who are supporting it are not necessarily oil and gas companies, but utility companies who sell gas. And they want to bring gas to customers. They want it to have a lower carbon footprint. What we're finding is that this costs money up front. Supplies are limited. The carbon accounting is complicated because it varies by the carbon intensity of the feedstock. This falls under the category for me of things that are good to do and use that as a learning opportunity. But even if massively scaled, at best, renewable natural gas is going to be like 6% of the gas supply, right?
Small, yeah.
Well, and so we're going to need other stuff. We're going to need to displace some of that gas with electricity. We're going to need to make synthetic natural gas. We're going to need to figure out ways to use hydrogen, but we can't continue to just keep using natural gas indefinitely. We will have to find alternatives, and this looks like a good place to start.
Let's move to the final story. Close to 30,000 people are displaced as Alberta is battling wildfires. So it seems quite early for mass evacuations from wildfires in Canada.
One of the things we've learned is that we're bad at predicting climate outcomes, and that we often underestimate specific impacts. Wildfires has been one of those. We had 33 million people displaced last year in Pakistan. We've got 30,000 people displaced in Alberta now. Very different reasons, but we're going to see a lot more of this. These wildfires cause enormous damage to ecosystems, enormous damage to communities, and of course, then vent carbon right back to the atmosphere.
Yeah, I just got back from Boise, Idaho, where I attended the Society of Environmental Journalists annual conference. And as part of that, I took a wildfire tour, which was fascinating, where we met with the U.S. Forest Service and smoke jumpers, the guys that jump out of planes, which was mind-blowing to me, to combat wildfires. And as we think of the cost of climate change, and there are ecosystem and real life and death costs and property costs, is the cost of fighting these things, right? Someone on the trip who was a reporter who's covered this a lot more closely than I had in the course of my career was just talking about how the share of their budget now devoted to wildfires is much greater than it has ever been. And there's consequences to that for other things that the Forest Service does.
Indeed. Well, with that, we will segue to our interview segment. That's actually a good segue. Now for our interview. Dr. Sue Natali is an Arctic ecologist who leads the Woodwell Climate Research Center's Arctic program, where she studies permafrost thaw. Woodwell Climate is a leading climate research nonprofit based in Woods Hole, Massachusetts, in the town of Falmouth. The group studies and then informs policymakers on causes and impacts of climate change across the globe. The center was founded in 1985 by ecologist George Woodwell, who was one of the earliest voices speaking out about the threat of climate change. In 1986, George Woodwell testified along with James Hansen and other scientists before the U.S. Senate Committee on the Environment and Public Works about the dangers of the greenhouse effect in one of the earliest public proceedings bringing widespread attention to the climate issue. Over 35 years later, Woodwell climate researchers are still working at the intersection of climate science and public policy. For our conversation today, we'll be taking an in-depth look at the thawing of permafrost, which, despite its massive implications on the climate system, is still left out of most climate models, which is a very, very scary thing. First, we'll cover some of the basics. What exactly is permafrost? Where is it? And how much land does it cover? Then we'll get into its interaction with the climate. How do warming temperatures affect permafrost? How much carbon does the permafrost contain, and how much could be released as the planet warms? Finally, we'll get into some of the implications permafrost thaw has on our lives and our efforts to mitigate the worst effects of climate change. So, Sue, tell us about your background. Describe how your career has led you to the work you're doing now at Woodwell.
I'm an ecosystem ecologist, and as an undergraduate, I was a biology major, and I kind of wandered around a bit because at the time I thought, well, I can either do science or I can have an impact on the world. And that was what I thought in my mind. And so I tried to work for, different nonprofits and try to go a little bit into activism world. And then I got my PhD in science. My focus was on looking at the effects of elevated CO2 on trace metal cycling. And so I was doing some work with mercury and other trace metals, and I started working in the Arctic because I was really interested in biogeochemistry, and so the cycling of elements, and that had global impacts, and that took me to carbon. I came to Woodwell because I realized that here was this place where you can do science and can have an impact, and that has really, really grown. I think even outside of Woodwell, there's a lot of other science and science organizations who are recognizing that science isn't separate from the way we make our decisions.
Tell us about the work that you're doing today, if you could.
The work that I do focuses on climate impacts on Arctic lands and impacts ranging from local impacts to the global implications of those changes. And so that means my focus is on permafrost and also whole ecosystem changes. And so just some context, the Arctic is warming quite rapidly, 3 to 4 times faster than the rest of the planet. One of the big drivers of this is the loss of sea ice. Mm-hmm. So when you have ice, it's very light and it reflects the sun's light back out and sends energy out. When you lose that ice, it's very dark and then it absorbs a lot of that energy. And so as a result, you have this regional impact. And we're particularly seeing the warming in the Arctic, especially in the winter and in the spring and in the fall, we're seeing accelerated warming. It's having a lot of impacts on Arctic people. So, the loss of ice, in addition to this albedo effect, it's impacting people's ability to access food resources, people's ability to get around on the land. And it's also, this accelerated warming is causing the permafrost, or this once perennially frozen ground, is starting to thaw.
So what is the definition of permafrost exactly?
Permafrost is ground that remains below 2 degrees Celsius for 2 or more consecutive years.
Okay.
That's its definition. So it's like anything that's in the ground, the soil, the ice, a rock, a frozen mammoth, anything that is in that ground is considered permafrost.
So describe the scale of that phenomenon. How much permafrost are we talking about, and why does that matter?
So permafrost underlies about 15% of the northern hemisphere land area. So it underlies a pretty large area. The impacts depend on where you are. So this is a really huge area with many, many different types of ecosystems. Overall, about 10 or 11% of the permafrost has thawed. It's a very difficult number to come by, I will say, right? Because unlike deforestation, you can see that from the satellite, permafrost is underneath the ground, right? And so we were relying on models and relatively, compared to the rest of the world, sparse kind of monitoring information.
Now, Sue, just so I'm clear, when we talk about the permafrost layer, does that begin at the surface and extend, or is this below the surface? And how far down does the permafrost layer extend?
Yeah, so it's below the surface, and the ground at the very surface where you have plant roots, that's not permafrost. That's called the active layer. So this is the area that thaws each summer. Below that, the ground never thaws in the summertime. And so that active layer can be anywhere from 20 centimeters to a meter to 2 meters. And then the permafrost thickness from the surface to the bottom of it can be meters to hundreds to 1,000 meters. Like it can be quite deep. So again, like it's this huge area, and there's many, many different ecosystems, and the temperature of the permafrost and the thickness of the permafrost is driven by a couple of things. It's driven by the air temperature, but it's also impacted by the ecosystem. So places where you have very thick organic matter, peat soils, those do a really good job of insulating the ground during the summer. And so you can have permafrost in areas that are relatively warm because you have this protective ground layer. And that protective layer is really important when we start thinking about what are the processes that are causing permafrost to thaw. So it is a little bit tricky when, we say where exactly is permafrost. Like there are some nice maps of permafrost, but it's difficult. You can't see it from the surface, and it is starting to thaw, and you can see the impacts of thaw from the surface if there's a lot of ice in the ground, because when that ice melts, the ground collapses. And it can manifest in different ways. There's many different types of ground ice. You can have massive ice wedges, and when those melt, then the permafrost thaws, you get like this very, very abrupt ground collapse, which you can see from satellite data. You can get just a very gradual kind of sinking of the ground, which maybe is not as dramatic looking, but, if your home is on that sinking ground, this becomes a very, very serious problem. Or if you're a coastal community impacted by sea level rise in this sinking ground. The other thing that happens is you can have lakes that drain essentially overnight, or like in a very short time frame. If you think about permafrost as this kind of like a concrete at the bottom of a swimming pool that then gets a crack. So if you're in a place that has drainage, especially in the warmer, lower latitudes of permafrost, there's lakes that are draining out very, very rapidly, and you can see them across the landscape. Vegetation changes are happening. If the ground sinks a little bit, it's getting wetter, and you're switching now from vegetation that grows on relatively dryish ground, although not many areas are dry, to areas that are now becoming wetlands.
And so why is this beyond draining lakes and collapsing ground levels and the other factors that you've already mentioned? What are some of the other reasons that we care about permafrost?
Yeah, so a big one is carbon. The permafrost region stores a lot of carbon. It's about 1.5 trillion tons plus, I would say, because it's not accounting for all the carbon pools, but about 1.5 trillion tons. And to put that in context, and I don't even know if this will be helpful, but what helps me is just thinking it's 3 times more carbon than is in all of the world's forest biomass. We think a lot about carbon in forests and the importance of forests, and they are very important, but like every tree and every forest on the planet, there's 3 times more carbon in permafrost. And it's like, we just can't see it, right? You see a tree falling and you're like, oh my gosh, we're losing that carbon, or fire, forest fire. But, we have all of this carbon that's just kind of sitting there.
In what form is this carbon that's stored in the permafrost? Like, are we talking about organic matter that's former roots whose decay was arrested because they were frozen? And then as it warms, in what ways would this impact emissions? Like, what would be the flux from the permafrost as temperatures were to warm?
So it's organic matter. Most of it is in the form of organic matter. So that organic matter can be roots that haven't fully decomposed, partially decomposed plants. It can be a whole piece of wood. And it starts to get tricky about understanding how much carbon will come out and in what form, partly because not all organic matter is equal. And I think about it sometimes like a banana is organic matter and a piece of wood is organic matter, right? And if you had both of those in front of you, like and you were hungry, you'd eat your banana like right away. The wood you probably wouldn't go after. And the same thing for microbes. Like some things they can break down really quickly, like a banana, but wood's going to take a while. And so one of the big challenges is understanding, like, one, how much carbon will be released from thawing permafrost, but the timing of that carbon and the form of that carbon is CO2. So what's happening is as microbes break down this organic matter, they use it as fuel, and byproducts are greenhouse gases, carbon dioxide and methane. If you are in a wetter environment, your microbes are more likely to produce and release methane. In drier conditions, carbon dioxide. One of the things that makes it even more like interesting, but also complicated in the Arctic is, as I said, places that are wet now may be dry in 10 years from now, and places that are dry now may start to sink and be wet in 10 years from now. So understanding this balance of carbon dioxide versus methane is quite tricky. And then the timing of what's coming out is tricky because, as I said, this is a really huge place, and the quality of that organic matter is really different. It depends on how the permafrost formed, what the quality of the organic matter was when it went into the ground.
As the permafrost thaws, do we have any idea of how much CO2 and methane is being released in terms of gigatons?
It might be up to about 10% of the amount of carbon that's in permafrost. This is the place where we do have this range. So anywhere from, say, 100 to 550 gigatons.
Wow.
So this is a cumulative estimate by the end of this century. So that high end, if we take the US's current emission rate and assume it continues to the end of the century, which it won't, it will decrease. That high end is higher than the US emissions, cumulative emissions would be by the end of the century. So it's substantial. Even on the low end, we're talking about emissions that are, on par with other greenhouse gas emitting nations.
So I've heard about, this sort of idea of that this is an accelerant, right, to the warming of the Earth. As as more release, the rate of warming increases, et cetera. Can you describe that effect?
As we warm elsewhere on the planet, right, like the temperature and greenhouse gases are globally mixed. So the more carbon that is emitted elsewhere, the warmer it's going to be in the Arctic, then the more carbon that's permafrost is going to thaw, then that means more greenhouse gases, CO2 and methane will be released. Those greenhouse gases, CO2 and methane then contribute to more warming. The big problem here is that we are not accounting when we're thinking about how do we stay below 1.5 or 2 degrees Celsius, when we're sort of adding up all of the budgets from these different greenhouse gas emitting nations, we're not adding permafrost into the mix.
Well, wait a sec. So the IPCC estimates about warming, the 1.5, 2 degrees, et cetera, these estimates don't include the effects of emissions from permafrost thawing. Is that what you're saying?
So essentially, but with the caveat, I will say the last IPCC report did include some permafrost, which is great. Before that, it had never been in any of the climate models. So, but most of the climate models, I think there were 11, that went into the IPCC report, only 2 of the climate models included permafrost carbon. And so when the IPCC report, it sort of uses these models as essentially kind of like averages them. So you can imagine if most do not include a very important processes, then on average, we're not going to be accounting for this. The IPCC report did also include a sort of rough budget for permafrost carbon emissions and thinking about our remaining carbon budgets, how much we have left to keep below 1.5 and 2 degrees Celsius. But what's important is that not only do most of the models not include permafrost carbon, the way that the models currently see permafrost thawing is a gradual top-down process. So air temperature, heat goes into the ground, and it's sort of gradually heating from the top layer down. The reality of permafrost thaw is that you have ice, and as we talked about, the ice melts, the ground collapses. That's called a thermokarst, but it's essentially abrupt ground collapse. When you have abrupt ground collapse, this can accelerate thaw because now the heat can go in from the top, from the side, right? You have this disturbance, and it may double the permafrost carbon feedback. So these abrupt processes are not in the models. The other important thing that's not in the model is fire. Fire is increasing everywhere. We hear this in the news, also increasing in the north. Important in northern regions because there's so much carbon below ground. When the fire burns, most of the carbon that's being released is carbon that's below the ground in the active layer, these roots. When you combust that surface, as I said, that surface is a really nice insulator in the summer. So it's essentially, you combust that, it's like opening the top of a cooler. So when you have fire and permafrost, when these are combined, it greatly accelerates permafrost thaw. And some of the work, that preliminary work that we have, modeling work that we have going on in my team here, suggests that the estimates of permafrost carbon emissions that were in the IPCC report, they may be 4 times higher than that.
Wow.
Because these really important processes have been left out to date.
So, Sue, why hasn't permafrost thawing been included in IPCC modeling?
So the models, these are Earth system models that inform the IPCC. Permafrost wasn't built into those models when they were developed. Like, they're very complicated models, and they are, and I'm not a modeler, but they're built to like represent the entire planet, right? That is like a non-trivial thing to do.
Right.
And then these complicated processes, disturbances, abrupt thaw, wildfire, again, it's not trivial. And essentially these different modeling communities really need support. And I just don't think right now the way science is funded, at least in the US, these relatively small grants for a small period of time, just hasn't been enough to make that happen. And so I think if there's a commitment from funding agencies, from governments to say, yeah, we want our models, our Earth system models, to truly represent important Earth system processes, then there needs to be proper funding to the modeling communities in order to do this.
So what we're talking about is this huge source of emissions that hasn't really been included in most climate models to date. What are the climate implications then of these permafrost emissions? What do we think the contribution is going to be?
Yeah, thinking about staying below 1.5 and 2 degrees Celsius, the amount of carbon that humans can continue to release to stay below those can be anywhere from 25% to half of that to the full carbon budget may be taken up by permafrost emissions.
Wow.
Now, the other thing to really consider about permafrost and other Earth system feedbacks is some of these things we're committing to, right? So even if we keep ourselves to 2 degrees Celsius, permafrost is kind of going to continue to thaw, and greenhouse gas emissions are continue to come out. And so it's really important when we think about 2 degrees C, 1.5 degrees C, overtopping those temperature thresholds and coming back down. We need to come down faster, right? Like, the longer we stay above 2C, and that's like additional warming that we're sort of buying ourselves into, that's going to come out of permafrost thaw. Those additional years of warming, in addition to the impact that's happening like at that very moment, those are leading to increased permafrost thaw.
Right.
And as that you have that increased permafrost thaw, you have this additional greenhouse gases that are coming out from permafrost into the atmosphere. The other thing is, it's not like a light switch, right? Like, even if we did turn off our air temperature warming, there's a lag, right? Like, there's a lag in the heat transfer down into the depths of the permafrost, and there will be a lag in that cooling. So you will still have this time period where you have this unfrozen ground or this warmer ground that can then be releasing additional greenhouse gases.
Right. My last question, Sue, I think, is you're doing this incredibly important work, but it's very depressing. It must be. Like, how do you deal with that?
I think, you do what you have to do, right? In some ways you compartmentalize it. There's a lot of really dedicated people who are on the front lines dealing with this, scientists who are studying this. So I think it's people are very inspiring to me, and that kind of like being around those people helps a lot. It is like, yes, we are destroying the planet, but it is an amazing planet, right? And so like, what do I do to sort of get out of this? Is I try to just get out in the world and like, you know, spend some time discovering the world, and that kind of wonder and beauty of the earth is what keeps me going.
Thank you so much, Sue. That was really wonderful having you today. Really appreciate you making the time for us.
Yeah, thank you so much.
That was Sue Natali, the Arctic Program Director for the Woodwell Climate Research Center, discussing the impacts of permafrost thaw on the global climate system and some of the broader implications this will have on our efforts to decarbonize. That's it for this episode of the Climate Now podcast. For more episodes, videos, or to sign up for our newsletter or register for an upcoming event, visit climatenow.com. We hope you'll join us for our next conversation. Climate Now is made possible in part by our science partners like the Livermore Lab Foundation. The Livermore Lab Foundation supports climate research and carbon cleanup initiatives at the Lawrence Livermore National Lab, which is a Department of Energy applied science and research facility. More information on the Foundation's climate work can be found at livermorelabfoundation.org.